Hello and welcome you all for today's session on part 2 of chemical kinetics. In the first part, we have observed that how to write the rate of a reaction, how to write the rate expression for a reaction, and graphically how to find out rate of a reaction and so on. In this part, we study about the different factors which affect rate of the reaction. And this is the point of study of this part. What are the factors that affect the rate of a reaction? The rate of a reaction is affected by initial concentration of the reactants. If the concentration are changed, the speed of the reaction also changes. To illustrate, there can be we take an example. Hydrochloric acid reacts with zinc and we get zinc chloride and hydrogen gas. The evolution of a gas is being seen in this reaction. Zinc chloride being aqueous and zinc being solid and this being aqueous. This is the reaction. To balance it, we need to write 2. Whatever. Now, in this reaction, evolution of hydrogen can be studied for the speed of the reaction. The volume of the hydrogen collected can be seen for the speed of the reaction. Suppose if you take 1 mHCl with 1 gram of zinc and 2 mHCl with 1 gram of zinc. If we do 2 experiments with changing the concentration of HCl, then we find that evolution of gas in this case is more than evolution of hydrogen gas in the first instance. This tells you that initial concentration of a reactant is important for determining the rate of the reaction. More the concentration, more is the rate of the reaction. Now, second factor is pressure. Pressure of the reactant is applicable when the reactant is a gas. More the pressure, more will be the concentration, and therefore more will be the rate of the reaction. Now, coming to the other factor, nature of the reactants. Nature of the reactants also determine the rate of the reaction. Let me take up an example. NO gas plus O2 gas will give NO2 gas, and carbon monoxide plus O2 giving rise to carbon dioxide gas. So both are a similar kind of reactions. But here this reaction is fast and the second reaction is slow. Even though they are similar, but speed of the reaction is different. It is because the nature of the reactant influences the rate of the reaction. Here, the formation of a new compound always involves formation of bond and breaking of the existing bond. So, in all such breaking and formation, energies are involved. Different amount of energies are needed in breaking and formation of bond. Therefore, rate also is being affected. Therefore, nature of the reactant again responsible for the rate of the reaction. Then temperature is another important factor. For most of the reactions, what we find is, if temperature is increased by 10 degrees Celsius, rate is increased 2 times. 2 times to 3 times. Therefore, even though the process is exothermic or endothermic, the reaction is endothermic or exothermic, we find that commonly by increase of temperature increases the rate of the reaction. Another important factor is catalyst. Catalyst affect the rate of the reaction. It normally increases the rate of the reaction. So presence of a small amount of catalyst will increase the rate of the reaction. Let us look into all these factors, how exactly it will affect based on different things. Now, first point is about the concentration. Let us take how concentration or initial concentration affects the rate of the reaction. So this rate of the reaction is determined by rate law. So rate law tells about how concentration change will affect the rate of the reaction. And what we find is rate of the reaction is directly proportional to concentration of the reaction raised to some power, and this power can be determined experimentally. For any reaction, rate is directly proportional to concentration of reactant to the power alpha or x, and this x or alpha can be determined experimentally, right? So this is called rate law. Or let us take an arbitrary equation: A moles of A plus B moles of B giving rise to C moles of C and D moles giving D moles of D. So here A and B are the reactants. Now the rate of the reaction is dependent upon A and B, right? A, B, C, D are the stoichiometric coefficients. Small a, B, C represent the stoichiometric coefficients of reactants and the products. Now, according to rate law, rate of the reaction is directly proportional to A, concentration of A to the power x, and concentration of B to the power y. And the rate of the reaction is therefore, from proportionality sign to equality sign, there should be a proportionality constant K. And this K is called rate constant. K is here called rate constant. Okay, this is experimentally determining it. X and Y are experimentally determined. And K is called rate constant. Now, suppose for a reaction, this expression, writing this expression for instantaneous rate we have seen in the first part. Now we can able to write rate of the reaction is equal to minus dR by dt if R is the reactant, and K into A to the power x and B to the power y. Remember that x and y may or may not be the stoichiometric coefficients of A and B. They are sometimes other than the stoichiometric coefficients of the reactants. And this is called differential rate equation. This is differential rate equation, and the law which tells about the relationship between this is called rate law. According to rate law, the rate of the reaction is directly proportional to product of concentration of reactants. Each concentration term is being raised by some numbers which are determined experimentally. Right? This is called rate law. Yes, for a general reaction, let us again take the general reaction. If this is the rate of the reaction, then K is called rate constant and x plus y is called order of the reaction. Now, how to determine the rate constant? To determine rate constant, let us take A is equal to 1 and B is equal to 1. 1 raised to x is 1 and 1 raised to y is 1. Therefore, this becomes 1. Then K becomes the rate of the reaction. So, this is how the proportionality constant, that is rate constant, is defined. Rate constant is equal to rate of the reaction. Rate constant is equal to rate of the reaction if the concentration of the reactants are unity. So, this is how it is being defined. Reaction rate when the concentration of each reactant is unity. Okay. So, this is also called specific reaction rate. Then the value of this is definite. This is definite for a reaction. For a temperature. It is dependent upon the temperature, but it is not dependent upon the concentration of A and B. So it is determined when concentration of A and B are unity. Therefore, if you change the A and B, K value is not going to change. Okay. Now, it dependent only upon temperature and catalyst. Presence of catalyst may change the rate constant value. Now, what is order of the reaction? As I told you, some of the exponents of the concentration terms in the rate law expression is called order of the reaction. So, this is the general reaction and this is the rate expression, and x plus y is called overall order of the reaction. It can also be told like this: it is x ordered with respect to A, it is y ordered with respect to B, and it is x plus y is the overall order of the reaction. So this is the way we can able to say the order of the reaction. Now, order of the reaction is always determined experimentally as exponential term. Exponents are being determined experimentally. X plus y also is determined experimentally. So these can be 0, 1, 2 or even a fraction. Order of the reaction can be a fraction also. So reactions are 0 ordered, first order, second order. In this way we call that. Right? The 0 order reaction means what? 0 order reaction means the concentration of that particular reactant doesn't affect the rate of the reaction. So rate of the reaction is not affected by the concentration of the reactant, then it is 0 order. So order of the reaction cannot be predicted by looking at the general equations. It is theoretical one, but it must be determined experimentally. So it may not be equal to the stoichiometric coefficients is the way that we have to understand. Now let us look into different reactions. 2NO2 plus F2 giving rise to NO2F. The rate expression determined experimentally is like this: K into NO2 to the power 1 and F to the power 1. Observe that 2 is the stoichiometric coefficient, but it is not present in the rate law expression. So this is determined experimentally, and 1 plus 1, it is order of the reaction is 2, or it is second order reaction. Now coming to this equation, 3NO giving rise to NO and 2O plus NO2. Here, even though 3 is the stoichiometric coefficient, NO to the power 2 is present in the rate law expression, telling you that it is a second order reaction. Let us look into this question, this example. 2NO2 giving rise to 2NO plus O2. 2 is the stoichiometric coefficient and same is being present. So this stoichiometric coefficient may be the exponent in some cases, and such reactions are called elementary reactions. So we understand it in this way: such reactions occur only in one step. There is no hidden steps, or it is not a complex reaction. So it is an elementary reaction. Those reactions which occur in single step are called elementary reactions, and in elementary reactions, stoichiometric coefficients will be the exponents of the concentration term in the rate law expression. Now in this case, H2O2 and iodide ion I minus and presence of acid, the rate law is expressed like this: rate is equal to K into H2O2 to the power 1 and I minus to the power 1. I minus to the power 1, and we find that H plus is not at all present in the order of in the rate law expression. Therefore, it is 0 ordered with respect to H plus. This is the way of understanding the expressions of rate law. Okay. Now, what are the units of rate constant? Whether the units of rate constant also change? Yes, it also changes depending upon the order of the reaction. Depending upon the order of the reaction, rate of the reaction also, rate constant, the units of the rate constant also changes. Now let us take a reaction of nth order. A giving rise to product is a general reaction, and if the rate law expression says that this reaction is nth order, then it can be written in this way. Now, what should be the unit of K? K unit, rate divided by A to the power n, or rate is nothing but concentration, concentration divided by time. Concentration, rate is nothing but concentration under unit time, and this A to the power n is again concentration to the power n. So rate, unit of rate is change of concentration over a period of time, therefore concentration by time. Or simplifying this, it is K is equal to concentration raised to 1 minus n and time raised time to the power minus 1. So this will help you determine the units of rate constant for different ordered reaction. Let us illustrate. So for the zero order reaction, moles per liter per second is the unit for rate divided by concentration to the power 0. So as the formula goes, for moles per liter per raised to 0 is 1 only. So it is moles per liter per second. So rate constant K has got the same unit as the order of the reaction. Right? For the second order, the unit is per second. And for the second order, it is liter per mole per second. So this is the way we can able to express the units of rate constant. Now let us see what is meant by elementary reactions. Let us take more examples on that. Now elementary reactions are those which occur in single step, those who complete in one step. See the reaction ammonium nitrite giving rise to N2 and 2H2O. This reaction occurs in a single step, therefore it is a unimolecular reaction. It is called unimolecular reaction. Decomposition of nitrogen tetroxide N2O4 to NO2. It is again a bimolecular reaction. Right? So reactions may be unimolecular, bimolecular, depending upon number of molecules involved. Number of molecules involved in the elementary reactions. Now, the one which is not occurring in one step is called complex reaction. So complex reactions have many steps where products are obtained after completion of sequence of the elementary reactions. Now let us take the example of the complex reactions. Before that, there is one more word to be understood, that is molecularity of a reaction. Molecularity of a reaction is simply the number of reacting species. Reacting species may be atoms, ions or molecules. Number of reacting species involving in an elementary reaction which must collide each other simultaneously to bring about the reaction. So it is a theoretical concept in which we consider the number of species that are colliding each other to bring about the reaction. So number that decides molecularity. Therefore, as I told you, so this ammonium nitrate decomposition is unimolecular reaction, and decomposition of HI is a bimolecular reaction. So these are all elementary reactions in which number of molecules involved determines the molecularity of the reaction. And 2NO plus O2, 2 plus 1, 3, tri-molecular reaction or termolecular reaction. Okay, so let us see what is molecularity of the reaction, and a question: why the reactions having molecularity greater than 3 are rare? Why the molecularity is rare? So just imagine a reaction in which molecularity is more than 3, then 3 molecules should simultaneously come together and collide each other to bring about the reaction. So always in a reaction mixture, if they have to collide each other simultaneously, more than 3 particles will become rare. Therefore, molecularity of the reaction will more than 3 will be rare. Okay, so chances, we are talking about the chances or factors that affect the rate of the reaction by because of the collision, chances of collision that is possible here. Then, so let us see this reaction. KClO3 plus 6FeSO4 plus 3H2SO4 giving rise to the product. So it seems to be a 10th ordered reaction because 1 plus 6 plus 3 is 9. Can the molecularity be 9? That means if a reaction is occurring like this, it may not be the 10th ordered reaction. It is experimentally when it is determined, it is second order reaction. It is a second order reaction. Now let us take the example of decomposition of H2O2. Decomposition of H2O2 follows these steps and we find that rate is equal to K into H2O2 to the power and I minus. Here I minus is not present in the product side, or in the presence of I minus this reaction occur, but still this is being taken in the rate law expression. Even though two molecules are there, but only to the power 1 is there. That means this reaction is a complex reaction and may not occur in a single step as it is seen from the reaction here. So there may be mechanism involved in the reaction. Mechanism means describing about the steps which are being followed by the reaction. Now this reaction seems to have two steps, or this reaction may occur in two steps. Initially H2O2, 1 mole of H2O2 reacts with iodide ion to give H2O and IO minus. This step after that is IO minus ion is being taken by H2O2 to give H2O, I minus and O. Now look at the overall reaction. I minus and I minus get cancelled. IO minus and IO minus get cancelled, and therefore 2 moles of H2O2 giving rise to 2 H2O and 1 O2, which is there as a product in the overall reaction. So the overall reaction, whatever is seeing, may occur in these two steps, and one of this step is slow. The first step is slow. So wherever the intermediate is being formed, this formation intermediate will have a lifespan, lesser lifespan, and therefore this reaction will be faster. Therefore, the explanation of the steps involved in the reaction is called mechanism of the reaction. A complex reaction will have mechanisms. Because of the mechanism, we can able to determine the rate law. Right? So rate law expressions are being substantiated by explaining in the slow step of mechanism. So since 1 mole of H2O2 and 1 mole of I minus is involved in the slow step, therefore these are being raised to the powers of the concentration terms in this expression. Right? So remember that slow step determines the rate of the reaction. Slow step. Whenever you are going in your vehicle in a single lane, the vehicle which is in front of you is getting slower, then your vehicle also will be at the pace with that. That means in a lane, the slowest vehicle determines the vehicles which are following. Slowest vehicle determines the speed of the vehicles which are following it. Similarly, if one of the step is slower, then rate of the reaction is affected by that slow step. Right? So in another instance that I may give you is, suppose a arrangement to flow of the water from top to the bottom is connected by differently sided wall. Okay. So these are all the legs or walls for the running water. This is 2 inch, this is 1 inch, this is 3 inch, and this is again 1 inch. So it is connected with differently sided diametered wall. Now the flow of the water is determined by the one wall which is having less diameter, because it controls the flow. Then even though there is 3 inch wall here, it will not get sufficient water to make the flow. Therefore, the slower step, similarly, the slowest step in a chemical reaction, slowest step in the mechanism determines rate of the reaction. Now, coming to the molecularity of a reaction, of a complex reaction, and molecularity of a complex reaction has no meaning until we understand that until it is a elementary reaction. A complex reaction is the series of two or more elementary reactions, right? So the complex completes in several steps. Complex reaction completes in several steps. The slow step determines the rate of the reaction. Slow step determines the rate of the reaction. And the molecularity of the slowest step, the stoichiometric coefficients of the species involved in the slowest step is being raised to the concentration terms of rate law expression. So that decides the overall order of the reaction. That determines overall order of the reaction. Now, let us see the differences between molecularity of the reaction and order of the reaction. Molecularity of the reaction, it is the number of atoms, ions or molecules that collide each other to bring about the reaction. So this is what we mean molecularity is. Order is the sum of the exponents of the concentration terms in the rate law expression. Now, which out of this can be zero? Molecularity cannot be zero, but order of the reaction can be zero. Molecularity of the reaction cannot be fraction, and order of the reaction can be a fraction. This is a theoretical concept that is experimentally determined concept, right? So this is a whole number, and molecularity can be a whole number, whereas the order of the reaction can be a fractional number also. Right? Now, overall molecularity of the complex reaction has no significance, and individual steps its own molecularity. Individual step has its own molecularity. Every step has got different molecularity for a complex reaction. But order of the reaction is for the overall reaction. Therefore, it is significant. Now, let us try to see how we can able to determine the rate constant value by one of the examples which is being taken here. There is an arbitrary reaction 2A plus B giving rise to C plus B. A and B are the reactants, and the reaction is being studied by variating the concentration of A and B. There were 4 experiments done by variating the concentration. When A is 0.1 moles per liter, B is 0.1 moles per liter, the initial rate is recorded like this: 6 into 10 to the power minus 3. So this is moles per liter per minute. That is the unit for finding out initial rate of the reaction. Now, by given this data, how we can able to find out the rate constant is the question. Now, for any reaction, we can write rate law. According to rate law, we can write rate is equal to K into A raised to X and B raised to Y. This is the general rate law expression. Now here, by experiment 1, by substitution the values, we can able to get one equation. Rate is 6.0 into 10 to the power minus 3. 6.0 into 10 to the power minus 3. This is the rate is equal to K into, when A is taken as 0.1 and B is taken as 0.1. And this X and Y are the powers which will remain as it is. We got one equation by substituting the values of A and B in experiment 1. Suppose if in another experiment, experiment 2, the values can be 7.2 into 10 to the power minus 2, which is equal to k into 0.3 raised to x and 0.2 raised to y. So this is second equation. Similarly, if we take the values of experiment 3, we will get third equation, that is 2.88 into 10 to the power minus 1 is equal to k into 0.3 raised to x and 0.4 raised to y. So this is third equation, right? And fourth equation can be got from experiment 4. So this is 2.40 into 10 to the power minus 2 is equal to k into 0.4 raised to x and 0.1 raised to y. So this is fourth equation. We got four equations by substituting the values of a and b and the rate value which are being determined experimentally at four different instances. Now we can find out the rate constant value and also the value of x and y that will give you the order of the reaction. So we have to determine the rate law implies we have to determine the values of x and y. Now look at the equations. You will get the idea how we can able to determine x value. To determine the x value, choose the y value which are equal. That means 0.1 raised to y and 0.1 raised to y is here. So dividing the expressions, dividing these equations, we will get the value of x. Now dividing equation 4 by equation 1. Equation 4 by equation 1. So 2.40 into 10 to the power minus 2 divided by 6.0 into 10 to the power minus 3 is equal to k into 0.4 raised to x, 0.1 raised to y. This is the fourth equation, divided by k into 0.1 raised to x and 0.1 raised to y. Now in this equation simplify that, k and k get cancelled and this get cancelled, 0.1 raised to y, 0.1 raised to y. Now only one variable is left out. 6 4s are, okay, 24. So to get 24 you have to do 10 to the power minus 3. Therefore this is 4. The value of this one is 4. And here the value is 0.4 by 0.1 raised to x. This is nothing but 4 raised to x. 0.4 divided by 0.1 is nothing but 4. And exponents are same, therefore 0.4 raised to x. Now if 4 raised to x is equal to 4, that means nothing but 1, that is x is equal to 1. So it is first ordered with respect to a. This is what you got. Now by looking at the two equations and dividing it by the other, we can able to get the value of y also. Now look at this. In these cases, in these two cases, this 0.3 raised to x and 0.3 raised to x is common. Therefore, if you do dividing equation 2 by 3, in this way, we are going to get the values like this. Dividing equation 2 by 3. Now, this is 7.2, 7 4s are 28. This value will be coming to be 1 by 4. The left hand side is 1 by 4. And this point, this gets cancelled and the k also get cancelled. And 0.2 by 0.4. 0.2 by 0.4 is nothing but 2 by 4. That is 1 by 2. 1 by 2 raised to y. So this is 1 by 2 raised to y. Okay. So 1 by 2 raised to y is equal to 1 by 4 implies 1 by 2 raised to y is equal to 1 by 2 raised to 2. Because 1 by 4 can be written in this way. So y is equal to 2. So x is equal to 1, y is equal to 2. So the order of the reaction is 2 plus 1, 3 is the order of the reaction. So hope it is clear. This is the way we have to determine the rate constant values. Right? Thank you, and we will see the next portion in the next part of it. Thank you.